People are still enjoying their spring breaks. Hopefully everyone turned in their homework number 4 yesterday. So just the one administrative thing, I will be posting the first phase of the project fairly shortly, probably later this evening or something like that. We won't have covered all of the material for that until probably sort of end of lecture this coming Thursday. But certainly at least some of the basic stuff you should be able to understand what's going on even as soon as I've posted it. But if all of the exact details aren't entirely clear right away, don't worry, we'll cover that all by Thursday. And we'll probably have that due probably about a week and a half from today. This first phase will be fairly straightforward. It'll be a lot more like homework versus a really involved design project. It's really to kind of get you started on just thinking about these types of problems. So it shouldn't be too bad. But as usual, start early because it will take you some time to actually do the design. Yeah.
What is the project?
Oh, so the project is going to be about basically a high-speed chip-to-chip communication system, which is similar to projects I've done in the past, but we're going to put a little bit of a twist on it, and that we're going to focus on slightly different aspects than we have in the past. And again, I'll be posting that very shortly. You'll see sort of all about that. But as I said, you won't understand exactly everything that I'm talking about immediately, simply because we're going to cover, hopefully by this Thursday, sort of introduction onto that general topic area. What are the key sort of issues and design things that you need to think about? The other thing I will mention is that the project is going to be in teams of 2. So if you haven't done so already, please do go ahead and grab yourself a partner now. You'll be needing that partner, perhaps not necessarily in this very first phase because things are fairly manageable, but very, very quickly the project will ramp up in both complexity and sort of the amount of stuff you have to do. So make sure you've got a partner and you've got someone identified already so that we're not sort of scrambling at the last minute to get people matched up. Having said that, if you do have an issue with figuring out someone to work with, let us know earlier rather than later so that we can try and help you out with that matching process. So other than that, any questions on either sort of homework, material, logistics, anything like that? Yeah?
How do you correctly bias a gain-boosting transistor?
How do you correctly bias a gain-boosting transistor? So let me just grab a slide here that has some empty space. Obviously, the title here is no longer relevant for the particular question that you just asked. Okay, so let's just do sort of the simplest conceptual figure, and then we can sort of talk a little bit more about the exact details as to how you'd really do it. Right, so at least conceptually, we sort of have always drawn our gain-boosted stage as looking something like this, right? So now, since you asked the question, I presume that if I ask you a question, you'll immediately know the answer. So why is it that this particular configuration is perhaps a little bit difficult in your particular technology? So why can't you just do exactly what I drew here, and why wouldn't that work?
Well, you want to get the right V star.
Okay. So you said it's pretty hard to get kind of the right V star, particularly on this device here, right? Now, in principle, you could try and do something where you kind of, let's say, mucked around with it in some sense. Because remember, this node here, in some sense, is really only defined by the VGS of this device here, right? Plus, of course, making sure that there's some sufficient drop across that transistor there. So what you could do is you could try and sort of, let's say, tweak it in some sense, so that once you knew what the VGS of this device was and how much headroom you really wanted across this device here, you could try and just size everything up such that the sort of voltage that landed here also happened to be a good bias for this transistor, right? However, having said that, that would basically constrain you so that this VDS here would, of course, have to be equal to the VGS of your gain-boosted stage, right? Which may or may not be exactly what you really wanted to do, right? Now, the trick is that I've drawn everything here in a sort of single-ended context. In reality, you might be doing this for a differential stage, right? And the good and the bad thing, quote unquote, about a differential stage is that you can actually introduce a tail current source here that gives you some more flexibility or freedom with what this actual common mode here might be. And in particular, I'll have to draw the sort of full differential stage, which I won't do it now. If you're interested, come and bug me afterwards. But basically what you'd probably end up with is you'd probably end up with something like a PMOS input stage that would essentially tolerate the relatively low common mode coming out of the basically drain of that input stage. Does that make sense? In other words, if I literally looked at this, and again, you have to sort of pretend a little bit that it's differential instead of single-ended, but basically if you set this VDS to be, let's say, a couple hundred millivolts, most likely that would imply that you'd want a PMOS input stage for your gain boosting just to tolerate that relatively low common mode. right? Because with the NMOS, it'd be really hard to fit both the current source and the VGS you needed for that NMOS input device. So most likely with a differential design, it's quite a bit easier to actually get that biasing going. With a single-ended thing, there's some tricks you'd probably have to play. You might have to level shift this or something like that to really get it to work properly. Does that answer your question? Or?
Yeah.
Okay, great. Other questions on either material or homework or anything like that? Oh, yeah?
So if you were, this is general, if you were basically trying to mirror current around to bias so you have an input current on NMOS and you're trying to mirror it around to bias another NMOS, would you just use sort of a 4-transistor mirror to basically pull the current around?
Oh, so the question was, let's say you had some input bias current, and you were trying to use it to bias, was it multiple NMOS devices? Or?
Yeah.
Okay. Yeah, so the simplest thing to do would actually be just use the same gate voltage, right? Now, this would constrain you to make the V star of all of these NMOS devices the same, right? Because if you're really trying to mirror them, then the current densities of all of those devices should be identical, right? Now, you may have a situation where, let's say that indeed what you actually wanted was you wanted one particular V star for that left-hand device here, but you wanted a different V star for that other right-hand device. In that case, indeed, what you would basically do is you'd build another current mirror, and in fact, another couple of current mirrors, and I'll just draw it, let's say, over here, where now this could indeed be, let's say, V star 1, right? And this other mirror over here could be V star 2, right? And indeed, if you needed separate V stars or really separate bias current densities, you'd end up having to do something like this. Where, of course, just this extra stage of mirroring is giving you the freedom to decouple those two V stars from each other. Does that answer the question? Sure.
What topology would you use?
Excellent question. So I would have tried to get away with just a cascoded topology, just because it's simpler and it's easier to design, and you can probably actually hit the gain that you wanted. But I believe we had a reasonably high gain spec there, so it may have caused you to, especially if you wanted to use a reasonably short channel device, you may have had to actually go for the gain boosting kind of thing. But I think we did it just reasonably enough that you probably could have gotten away with a cascode topology. And it looks like a few people are shaking their head saying, yeah, I got it to work with cascode, so that's probably what I would have done. If you did gain boost, by the way, that's not to say it was bad. That's totally fine. It's just easier to design with a cascode, obviously. All right, great. Any other questions? Or? All right, so if not, let's go ahead and dive back into the material. And where I believe you guys ended up last time was basically on this last slide here, talking about with a multi-stage amplifier that you've applied Miller compensation to, or particularly I shouldn't say multi-stage, I should say two-stage, that you've applied a Miller compensation to. Where I think you basically ended up was kind of with pointing out the fact that because the zero, or that feed-forward zero in the Miller compensated design, is really just set by essentially white ink usually is not particularly useful. There we go. Because that feed-forward zero is really set by GM2 over CC, right? And your, of course, bandwidth, or your unity gain bandwidth, is set by GM1 over CC. Then what basically ended up happening was that you were kind of stuck in terms of where that zero was sitting relative to unity gain bandwidth, unless you just basically wanted to end up spending more power in that second stage, right? And the reason we said that we really didn't want to do that is that that power we spent in the second stage wouldn't help us whatsoever from a settling standpoint, right? All it would do is maybe help our stability because of that feed-forward zero, but otherwise it's kind of wasted, right? Because remember, at the end of the day, especially when you do all those design methodologies, your power should really just be fixed by how fast you need to settle things, and not hopefully by DC gain or stability or these other types of, let's say, quote-unquote, secondary considerations. So we said this is really kind of bad, and it would be nice if there was a way around it. Okay? So hopefully, as you guys all saw in EE 140, indeed, there's a fairly simple trick that you can play to essentially eliminate the effect of that right half plane zero. And so the simplest, sort of, or most common one is the so-called nulling resistor. Okay? So to draw how that looks, let's just pretend we have our simple two-stage amplifier. So that's our first stage. This is, let's say, our second stage. Okay? And the idea is quite straightforward. So instead of just having that CC by itself, we're going to add in an additional nulling resistor or feed-forward resistor like this. Okay? So as the sort of text on the slide is indicating, it's saying that by adding that resistor in, we're somehow limiting the feed-forward current at high frequencies. Okay, but before we sort of get into any of the math or anything like that I've drawn here, why is it that adding this resistor from a purely intuitive standpoint, why is it that this might help with the standpoint of the right half plane 0? What is it sort of conceptually trying to do? Okay, so you said push the 0 all the way to infinity. You're potentially correct, and there is a way to do that. We'll talk about that in one more second. But I want the very, very intuitive sort of answer. And so, yeah. That's correct. It reduces the maximum current that actually can go through that path. But by the way, why is it that having current flow through that path, and in particular flow from left to right, why was that bad? Why did that cause the right half plane 0 in the first place? There we go. So that's exactly the trick, right? Remember, if you just had that capacitor there, then at DC, what happens is that you apply some wiggle at this gate voltage over here, and you get the opposite phase at the drain of the NMOS, right? But at high frequencies, if you're just going directly through that capacitor, then the sign of the, if you wiggle over here, you get the same sign of wiggle on the other side. Remember? So that's actually exactly what caused that right half plane 0. It was the fact that at low frequencies, you had basically a 180-degree phase shift, and at high frequencies, you did not. Okay? In other words, that's what's making that 0 sit in the right half plane instead of the left half plane. And if you remember, right half plane zeros are really, really bad because they increase your magnitude and give you phase shift, right? So stability-wise, they're always really, really nasty. Okay? So the whole trick here is that by adding that feed-forward resistor in, what we're really trying to do is make sure that you can never get enough current flowing through that bad path or through the path that would cause you the additional phase shift to actually flip the sign of the gain at the output. Okay? So as we said a second ago, you can actually even try and calculate what does that resistor need to be in order to make sure that there is never sort of this effect from the 0. In other words, that right half plane 0 just completely goes away. Okay? And so this is actually very similar to sort of some of the examples we looked at before, where now what we're going to think about is, again, this is really happening when that CC has effectively gone to a 0 impedance or a very low impedance. So we can just try to kind of draw an equivalent model that will show us how would we choose that feed-forward resistor, RZ, such that I can never actually get this output over here to change its sign. And in particular, if I want to get rid of the 0 completely, then what I want to have happen is that if I wiggle this input over here, then basically nothing will happen at that output over there. Right? In other words, there will be no change in the voltage whatsoever. Because notice, by assuming that this has happened at a frequency where CC is basically a short, if I make it so that even after this is shorted, there's no effect on the output, then that means that the 0 really has gone away. All right? So the simple way to have that happen would just be to say that if I look at the current basically flowing through the resistor, right? If I want to make sure it has no effect on the output, then that had better be equal to the current flowing through the transistor, right? And let me just call that IGM instead. Okay? So in other words, if I want to figure out what value of resistance I should choose to make that right half plane 0 just completely go away, which by the way mathematically is equivalent to saying that that 0 is off at infinity, okay? Then I just have to set these two things equal to each other. In other words, I just have to say that the current from the GM is equal to the current from that feed-forward resistor. Okay? And if I just come up with some fictional input source right there, then of course the current through the resistor is just going to be VI over RZ. And I want to set that equal to GM times VI. Okay? Which hopefully should be very obvious, and this is probably something you saw before. It just says that you will then want that feed-forward resistor to be equal to 1 over GM. Okay? Because again, if you do that, that will actually push that right half plane 0 out to an infinite frequency. Or to say it again a different way, there will be no more right half plane 0 at all. Yes? Yes, I'm ignoring the output resistance as I typically do, right? So this is somewhat simplified, but usually this is actually a pretty, in fact, actually it turns out, even if I was to include the RO, it wouldn't actually change anything for this particular question. Because notice what I'm really trying to do is say, under what condition will it be that I have no change in current flowing into my output load as a function of the input, right? And no matter if, independent of whether there was an RO over there, what I'm still really trying to do is just to make sure that as a function of this input here, the current due to the resistance is exactly balancing the current due to the GM. In other words, I could always take another, load impedance in parallel over here, and it wouldn't really change the result. Because again, the way I even got this in the first place was by saying that there was no change in the voltage at the output at all. Right? And in order for that to be true, again, I can put any impedance I want on that side over there. Because it's not affected by VI directly, it doesn't matter what that value is. It's a good question. Other questions on this? Or? Okay, so turns out you can actually do some pretty aggressive things with this. You can even try and make it so that you don't just actually cancel that right half plane 0. You actually try and bring it all the way back to the left half plane and start trying to cancel some other poles. But long story short, don't do it. It's pretty, it's one of those things that it sounds really good, but then you try it and it doesn't actually work that well because things aren't as well controlled as you'd like them to be. So the typical choice is indeed to just try and push that right half plane 0 out to infinity. The other thing I should mention is that you do have to be a little bit careful because now that you have this resistor here, right, there's going to be another pole just coming from essentially that resistor with the internal capacitance of your circuit. Okay? So this is going to add a third pole there. So you have to be careful about that third pole to make sure that it doesn't end up at a point that would affect your overall stability and performance and etc. Okay? But nonetheless, this is a pretty powerful and common technique, particularly for these Miller compensated types of designs, because it really does allow you to decouple that right half plane, or rather just get rid of that right half plane so that it's not having a bad effect on your overall stability. Does this make sense to everybody? Or? Okay, great. So I do want to sort of spend a little bit of time just sort of thinking a little bit more carefully about exactly how you'd actually build that nulling resistor. Okay? So let's again just go and draw our very simple two-stage amplifier. So again, we have, let's say, our first stage like this. Then let's say we have our second stage like this. And just as an example, I have my coupling, my compensation capacitor there. And then this is my resistor. And then just as, let's say, an initial choice, let's say that I make this out of a polysilicon resistor. Okay, so as you remember, as we talked about, we could take sort of an unsilicided piece of poly and build a resistor out of that. So now, let me ask you guys, who thinks that that particular choice for how I built the resistor is a good or a bad choice? Let's maybe take a vote. So who thinks that that's a good choice? Bad choice?
Can I ask a question first?
Sure.
What happens if you don't exactly match resistances?
Okay. So the question was, what happens if you don't exactly match the resistances? So now I'm going to turn it back around on your colleagues. What happens?
I think it sort of depends how poorly you match them. You're moving the 0 to some higher frequency, and as long as you get it high enough, typically you would be okay. But if you don't hit the 100 GM exactly.
Okay, great. So that's exactly what happens, right? So what happens is we said that ideally we wanted our nulling resistor to be equal to 1 over GM2, right? Well, if it doesn't exactly equal it, there's kind of two cases, right? In one case, it'll basically mean that your right half plane 0 will still exist, but will just be at some hopefully reasonably high frequency. And it turns out that actually in the other case, what will happen is it'll become a left half plane 0, but it'll start coming back in. In particular, as you increase the resistance, it'll basically push it all the way to the left half plane and then start coming back towards lower frequency. Okay? So it is true that you're perhaps tolerant of some variations in that nulling resistance. So as long as those variations are relatively small in comparison to 1 over GM, then you could maybe argue that, okay, yeah, it's kind of a reasonable choice. But so now let me again turn the question around on you guys. if this is really what you wanted it to be dependent upon, in other words, if you really want the nulling resistor to be equal to 1 over GM, how do you think you should actually build that resistor? What's a good way to mimic a 1 over GM? Yeah, okay, so you said a diode-connected transistor. Really, to say it another way, a transistor, right? Now, by the way, if you really did a diode-connected transistor here, right, there's potentially some issues because that doesn't exactly match my model of a resistor, right? But that's one way of trying it. So it turns out in reality what you'll typically do is instead of building it out of a piece of polysilicon, indeed, ideally speaking, what you'd basically do is build it out of a transistor, okay? So ideally speaking, if life was really perfect, then what you'd actually do is you'd take that transistor there. You typically have to run this thing in triode, right? Because you actually want it to look like a resistor, not like some additional stage of amplification. Although we'll come back to that in one more second, right? So if you really want this to look like a resistor, then you'd basically bias the thing so that it's again in the triode or linear region of operation, which would imply you'd need some magic, let's say, gate voltage to get it to basically, first of all, act in triode, but second, so that its GM would indeed track with the GM of that output device, right? In other words, as long as you used some magic VGS here that made the GM of that the same as the GM of the output stage, then indeed life would be good, okay? Turns out, practically speaking, that's not always so straightforward to do, because you have to sort of come up with a GM here that somehow, let's say, the VGS of this device plus the nominal bias of this point. So more common choice is to say, well, okay, I'm not going to get this exactly right, but maybe I'll just sort of tie this as an example to VDD, which, by the way, it turns out that especially in these modern technologies, the VG you would have wanted to use would have been outside the power supply rail. So you just tie it to the highest thing you can. And then the other thing you'll typically do is you'll say, well, okay, again, this isn't perfect, but I may actually need to use sort of the PMOS device as well, simply because if this bias point is really sitting somewhere around VDD over 2, it's hard to get a nice, large enough bias across either the NMOS or the PMOS device. So you kind of try and put them both in parallel to get something that'll work across a reasonably wide range of input voltage. Okay? The bottom line of all this is not to say that this is going to perfectly track. Indeed, it's actually going to be different. But it's going to be a lot better than the poly resistance. Because to the extent that something just changes in the process, let's say the oxide thickness, the mobility, or something like that, it will at least affect the transistors the same way, or I should say the resistor, in a similar way as what it does to the actual transistors in your amplifier, right? Whereas with a polysilicon resistance, the variation mechanism is just totally decoupled from each other, right? There's no particular reason why something that changes the GM of this transistor would have any specific effect on that polysilicon resistor. Does this make sense to everybody? Or? So by the way, keep this general idea in mind because we're about to talk about biasing and references in 1 second. And the most important idea in that sort of category of circuits is actually to realize what it is that you want to track against what. Okay? Yes?
Why does having the basically cascade configuration allow you to track GM over wider?
Oh, so all that's happening here is you just need this so-called full transmission gate topology, simply because if this node here is actually swinging by a reasonably large amount, then it's going to be pretty hard to guarantee that that transistor actually stays, let's say, in the region you wanted it to be across that entire input voltage swing. That's all. That's not to say, by the way, that having a PMOS device here is necessarily a good thing, because PMOSs and NMOSs could move differently from each other. So obviously the tracking of this would be worse than what you could have potentially gotten from just having the NMOS device. But this is more just of a, let's say, practical thing of making sure that it actually works across the full voltage range. All right, great. So, unless there's more questions on that, turns out that there's a bunch of other tricks that people have tried to come up with, also to get rid of this right half plane zero effect. And they're mostly sort of motivated by the fact that even though I could indeed play this nulling resistor trick, it's hard to really get it to track exactly with what you wanted it to track against. Meaning, it's hard to really make it in a way that indeed ideally tracks with exactly the GM of that output stage. So, almost all of the sort of following tricks that I'm going to, or techniques that I'm going to talk about, are all based on one very simple realization. Okay? So we said in the beginning, the whole reason this right half plane zero happened was that if I think about my conceptual two-stage amplifier, and again, I'll just sort of draw it on the side over here. All right, so I've got my first GM stage that has some negative gain. I've got my second GM stage that again has some negative gain. And then if I just have the capacitor by itself, then again we had one path that had negative gain, and then a second path that had the opposite sign of gain. Right? That's what was causing that right half plane zero. So almost all of the, in fact, all of the techniques I'm going to talk about now are based on saying that, well, okay, if instead of allowing that thing to actually have a path that goes through the capacitor from left to right, why don't I instead add in a buffer that makes it so that now I only get signals flowing from right to left? Okay? In other words, I'm trying to stop any path directly from the input to the output. Right? Because remember, the whole reason you wanted this compensation capacitor was for the feedback path and not for the feed-forward path. Right? So indeed, if I can just add a buffer here, and if you'll pay close attention, you'll probably realize that the gain of this buffer needs to be positive to make sure that you haven't changed the sign of the feedback. Right? As long as that buffer is unilateral, meaning it really only allows signals to flow from the right to the left, then indeed I can actually get rid of that right half plane zero. Right? This will now really be acting almost as ideally as I expected the Miller compensation to be acting. Right? It'll just act as effectively a larger capacitor rather than also having that feed-forward path. Okay? So the first person who described this in some level of detail was a guy named Ahuja. This was presented in the Journal of Solid-State Circuits, I believe, in December 1983, so quite a while ago. And indeed, in terms of getting rid of that right half plane zero, it's very effective. Okay, so let me just sort of show you the circuit that he built here. So this first stage is just a simple sort of current mirror-loaded differential OTA, right? This is actually the second stage of the amplifier right here. This is just a common source. And then what he did was, again, this was your compensation capacitor CC. What he did is he just added this essentially common gate amplifier to act as a buffer from that feedback from the compensation cap back to the input of the second stage. Okay? So in other words, this thing right here is literally just that buffer that I drew in black right here. And these are just the two OTA stages. By the way, this is a PMOS device in case it's hard for you to tell. Okay? So again, this is exactly sort of just trying to utilize this idea of if you make the feedback through that compensation cap unilateral, you can get rid of the right half plane zero. Now, unfortunately, it turns out that this was not a particularly popular approach. And that's why you probably have never heard of it before. By the way, this is often referred to as cascode compensation, just in the sense of this common gate amplifier is kind of like a cascode. I'll show you another version in one more second. But basically, it turns out that this is not very popular because, unfortunately, it still costs you quite a bit of power to actually make it work. Okay? And the reason for that is the following. So let's imagine that I'm under the condition where I apply a really big input into the amplifier, so that I'm now going to be slewing my compensation cap. Okay? Well, if, for example, I apply an input such that, as an example, my left-hand side of the amplifier there is just totally off, and the right-hand side is basically driving the full bias current like this, okay? Then what's going to happen is that that node right there will basically go to kind of the highest voltage that it can, which would mean that this transistor here will just be turned off, right? So that means that now if I'm sort of interested in how fast I can actually change my output, the only thing that's actually changing the output is just that current through CC right there. Or rather, I should say, the only thing that's going to allow me to change the compensation cap is this bias current that I applied into that buffer amplifier. Okay? So the reason this is bad is that now what this basically says is that indeed if I ever get into this slewing condition, then I have to make sure that I size this current here large enough that I can actually slew that compensation cap fast enough to hit my settling time requirements. Okay? And unfortunately, that typically means that this bias current here has to be reasonably large. Or rather, I should say reasonably large in comparison to the main bias currents that are actually sort of buying you something from a settling or just otherwise even DC gain standpoint. Okay? Does this make sense to everybody? Or? Exactly. So if this buffer was not here, right, if you just connected that compensation cap directly from the drain to the gate of that output stage, then now you'd actually get the full I1 of the OTA slewing that capacitance. And remember, this I1, you were going to be setting that thing to be a certain size in order to do your settling in any case, right? In other words, current you spend on I1 is exactly the current that buys you settling time, right? Whereas current you spend anywhere else doesn't buy you settling time. Or rather, ideally speaking, should not be affecting your settling time. Does this make sense to everybody? Or? Okay, so again, nice trick, conceptually good idea, but unfortunately doesn't quite get us what we want, which is a nice way of building the amplifier so that we don't have to actually spend any extra power in order to get rid of this right half plane zero. So there's another version, which was proposed by a guy named Ribner about 1 year later. So this was actually also in the Journal of Solid State Circuits, and I believe this one was also in December, but just in 1984. Okay? And the idea is quite straightforward. Okay? So he's basically going to apply the same technique where he's going to use a common gate device to act as a buffer. It's just he's going to try and do it in a way that's going to reuse bias current he needed to have anyways. Okay? So let me just show you how you would do that. So let's pretend that you build, again, one of these multi-stage amplifiers. But now let's pretend that we actually build it with a cascode in my first stage. Okay? And just to make my drawing easier, not necessarily that this is a particularly practical way of doing it, I'm going to assume that my second stage is a PMOS device. Okay? So let's say that this was my sort of overall amplifier where, of course, the output would have been over here. Okay? So if I was doing a traditional Miller compensation, then I would have put my capacitor like this, right? I would have just tied it from the output directly back to the input of that second stage, right? All right, so now can anyone see a sort of, and actually let me just be perhaps a little bit more clear. There's going to be some bias voltage here. This is, of course, going to be the input voltage. Can anyone see a somewhat, let's say, clever place you might be able to connect the compensation capacitor that actually has this very similar effect to that buffer we drew in the previous example? Okay, when you say between the cascode, let's just, maybe list out the two terminals. So one side of the compensation cap is what, and the other side is what? You did say the right thing, by the way. I just want to make sure we're clear.
So one terminal is between the source and the drain.
Okay. Oh, sorry. Let me do that in a different color. There we go. Okay, so one is going to be here. Where's the other?
Where it is now.
Yeah, exactly. It's just going to be V out, right? So notice by doing this, right, I still have feedback from V out back to effectively the input of that amplifier, right? Because essentially anything that flows through here should just go back through the cascode to this gate, right? It's just indeed acting just like the feedback we had before. But now, if I look at current coming from that input transistor, as long as the 1 over GM of that cascode device is sufficiently low impedance compared to this coupling cap, then indeed all of that current should be flowing through the cascode device and not through the compensation cap. Okay? So in other words, this is almost identical to the picture we drew over here, and let me just get rid of some of these things so it's more clear. It's almost the same as just using a common gate buffer to try and unilateralize that feedback path, right? But now what I've done is I've done it in a way that I'm reusing this bias current here, right? I don't actually have to spend any additional bias current on this cascode device itself. Okay? Yes? It's not that there's zero current there. It's only, and by the way, the question just for people watching was, why is it that there's no feed-forward path at all? It's not that there's no feed-forward path at all. It's just that, again, as long as the 1 over GM of this cascode device is sufficiently low impedance compared to that capacitance, then the current from the input will flow through the cascode device and not through that capacitance. Okay? So this is kind of the standard cascode argument as, as long as the impedance in the cascode is low, all of the current should be flowing through that cascode and not through the other potential paths that are there. Okay? So again, actually very, very clever trick. Turns out to be not super popular either. So now, let's see if you guys can figure out why is this not particularly popular? What's potentially really annoying about this thing?
If you make the GM of the upper device big, then your initial stacking full at a very low frequency.
The GM of this device, you mean, or
With the CC,
or this one?
but the
Oh, okay. So you said that, if I make the GM of this really, really big, then I might be adding a pole at low frequency. So which pole, what would be causing that? Okay. So let me maybe rephrase what you're saying a little bit, and I think you are actually getting at the right point. So, or let me actually maybe ask you guys to see if you can get it. How many poles do you guys think this structure actually has? Is it just 2, or is it more than that? And by the way, remember, there's always some parasitic cap right here. There's always some load cap right there. So how many poles does this structure have? Yeah, there's 3 poles, right? Because there's a pole there, a pole here, and a pole at that source node right there. So indeed, what DJ was perhaps getting at was that, unfortunately, with this particular design, as you change that CC, you're not just going to be sort of changing where the dominant pole is. You're also actually going to be changing where this third or let's say second non-dominant pole is going to be sitting, right? Because obviously that second non-dominant pole is very much tied to the GM of this Cascode device and how big you made that CC, right? So the problem with this is not that you can't potentially get it to work. You probably can in many situations. The problem is that it's really hard to actually understand exactly how to design it. Because fundamentally, when you change that compensation cap, you're not just sort of mucking around with that main dominant pole, which is usually what you want to control. You're also moving that third order pole around. Okay? And when you move that third order pole around, if you're not careful, it can land in places where you don't actually want it to be. Okay? So the real point here, the take-home message is not that you can't actually do something like this. It's just that it's typically enough of a pain in the ass that people don't want to deal with it. Okay, there's a complicated enough design procedure that people just say, you know what, forget it. I'm just going to stick, for example, with a nulling resistor type of implementation. Does this make sense to everybody? Or, by the way, if you don't believe me, either go check out the paper, or perhaps even better, just try and write out what the sort of transfer function of this whole structure is, and you'll very quickly see that as you change CC, you're changing all kinds of things all at once. So it ends up being pretty difficult to really precisely say, yeah, I want CC value of this in order to get a certain either stability or dynamic settling out of this particular design. Okay. So just a couple of sort of, let's say, last things that I want to talk about in the context of these multi-stage amplifiers before we move on. So the first is that, obviously with any amplifier design that we're doing, we need to be able to understand what the noise performance of that amplifier will be. Okay? So let's go ahead and actually do a somewhat simplified analysis for these 2-stage amplifiers. Now, it turns out that when you really go and you build these 2-stage amplifiers, you can pretty typically have anywhere from like 30 to 40 transistors or so. So clearly we're not going to want to sit there and write small signal equations for each and every single one of those. Again, we're going to want some relatively simple way of understanding what the dominant contributors will really be. So to do that, let's again just use our very simple sort of model for a 2-stage amplifier. So we'll have our first stage, as usual. We'll have our second stage like this. And let's continue to assume that we use some sort of Miller compensation like that. Okay, so let's just call that CC. And of course, we'll also have a CL right here. Okay, and this will be our output voltage. Now, as usual, we're typically going to use this in some kind of a feedback configuration. So let's assume that actually we're going to feed back to here some F times the output voltage. Okay, where F is, as usual, our feedback factor. Okay, and notice there's a minus sign there. I had to add the minus sign because obviously now with the two negative gain stages in Cascade, this is actually positive from here to there. Okay? Okay, so as usual with all of our noise analyses, I can just take this sort of simple circuit, and the first thing I will do is draw the small signal model, right? So let's go ahead and do that. So for that first stage there, notice I put that minus sign in the front, so I'm just going to point the current source the other way. So we're going to have a GM1 times F times V out. Okay? I'll have some V1 right here. And as usual, I'm going to ignore all the output resistors and things like that. I'll have my CC here. Then I'll have my GM2 times V1. And I'll have my CL right there. Okay, and of course, this will be the output voltage. Okay, so this is just a small signal model. I haven't drawn any noise sources or anything like that. But I wanted to draw this already just to point out that obviously now, since I didn't put any feed forward, nulling resistor or anything like that, again, I'm going to have this annoyance with that feed forward path. Okay? And trust me, you can do the noise calculation including that feed forward path, but it's a pain in the butt. Okay? So what I want to do now is come up with a simple approximation that should still give me a very reasonable guess as to what the actual noise performance will be, but will make it a hell of a lot easier to actually calculate what the sort of, all those noise integrals and things like that end up being. So what was the sort of, simple trick that you guys learned, hopefully back in EE 140 or perhaps even in 105, where if you had a Miller compensated amplifier and you didn't want to deal with it, doing these full set of equations, what was kind of the simple approximation that you were always taught to do?
Multiply by 1 times the gain part, and then split the compensation capacitor.
Yeah, so exactly. So the whole trick was what you're typically taught, and by the way, I'll do something very similar, although not exactly the same. It's usually called the so-called Miller approximation, where you'd basically take that compensation cap and split it onto the two sides, right? You'd have one piece show up on the input side, and another piece show up essentially on the output side, right? So again, I'm going to do something very similar, although ever so slightly different. So on the output network, I'm actually going to do sort of precisely the same thing. I'm going to say that indeed there's a CC to ground like this, which again is not correct, but it's just my approximation. Okay, I'll have, of course, my GM2 times V1. Okay, I'll have my load capacitance there. And now I'm just going to add in the noise current, just to be clear that indeed we're going to have to include that eventually. Okay, so that's my output side. Then on the input side, again, I'm going to do something very similar, but just slightly different to get a slightly more accurate result. So I'm still going to have my GM1F V out. Okay, and of course this is V out over here. I'm going to have my noise current, which let me just call that IN1. Okay? And then what I'm going to do is I'm going to have that CC, but I'm still going to include the fact that this is actually being driven by V out. Okay? Or rather that the other side of it is V out. And just to be clear, this is of course V1 right here. Okay? So the reason I've done things this way is by doing it, I can indeed include the effect of the feedback. It's just that I've gotten rid of the feed forward effect. Right? So notice there's no path basically directly from here to the actual output. Right? So this is still going to be reasonably accurate. I'm just losing the effect of that feed forward 0, if there was one. Okay? As we'll see this actually, or rather you can try this yourself at home. You'll see that if you really do this approximation, you'll still actually get very, very close to the right answer, especially under the conditions that you've built this thing in a way that will ensure it really is stable at the end of the day. Okay? Does this make sense to everybody? Or? Okay, so once you've gotten everything into this form, you can do sort of basically 2 sets of KCL, or 2 equations driven by KCL. Of course, one at this node and one at that node. And you can basically just go and figure out what those transfer functions are. So because that math is not particularly interesting or helpful, I'm basically just going to show you what the result ends up being. Okay? So if you go and you write that KCL, you take that model that I showed you, what you'll end up with is something that looks like this. So you'll say that the output voltage is equal to 1 over F times GM1. So this is kind of like just a resistance. And hopefully that makes sense why that's sitting there. It's very similar to the single stage amplifier was. Times some kind of filter, okay? Where I've sort of given you, the coefficients inside of that filter. Again, the details there are not super important. We'll sort of come back to them in 1 second. Times essentially these 2 contributions from the 2 noise current sources, okay? So IN1 again is just the noise current from the first stage, and IN2 is the noise current from the second stage, okay? And again, I've just written this thing in this sort of standard form of the filter so that I can do my, as usual, the integrations the way that, you've seen hopefully many, many times already now, right? So if indeed you do those integrations, you'll end up with the following result. Okay? It'll basically tell you that the total noise at the output is just KT over CC times gamma over F plus KT over CC plus CL times gamma. Okay? Where as with before, this is the noise from the first stage. Okay? And this is the noise from the second stage. Okay? Now, just to make things maybe a little bit more clear or intuitive, I'm just going to rearrange this expression slightly to sort of make it so that it's the noise from the first stage times 1 plus some factor. Okay? Where that factor is like the relative contribution of noise due to the second stage. Okay? So if we just pull out this KT over CC times gamma over F, then the overall noise just becomes that times 1 plus FCC over CC plus CL. Okay? Now, the main reason I did things this way is that if you pay close attention to this thing right here, as long as you're doing, let's say, a typical feedback where your feedback factor is less than 1, this overall piece here is guaranteed to be less than 1. Right? In other words, the contribution of noise due to the second stage is guaranteed to be less than the contribution of the first stage. Okay? And that's kind of a good thing, because remember, at the end of the day, it was always your first stage that you actually wanted to be dominating in terms of your performance. Right? That second stage was really just there to add some additional gain at DC. And so any noise or sort of slewing limitations or anything like that that it adds would always have been bad news. Okay? So at the end of the day, we still have actually a pretty nice and fairly simple result. So let's assume that indeed you've done things in a way that, to zero order, to a reasonable extent, that second stage doesn't actually dominate your noise contribution. What this basically tells you is that your overall noise performance, or your overall noise at the output of that two-stage amplifier, is just KT over CC times gamma over F. Okay? So notice this is actually almost identical to your standard single-stage amplifier, but with one very big difference. Right? The big difference now is that rather than your noise being set by KT over CL, meaning the output capacitor, now it's actually set by KT over CC, the compensation capacitor. Okay? Now, in some senses, this should have been kind of expected, because remember, the whole reason we ended up with sort of, these KT over C kinds of things was that in the single-stage amplifier, it was the load cap that was actually setting the bandwidth of the output. Right? In this Miller compensated design, it's actually the compensation cap that's setting the bandwidth. Right? And so because of that, again, makes perfect sense that your noise is now set by compensation capacitance and not by the output capacitance. Does this make sense to everybody? Or? Okay, so just one last sort of quick thing before we move on and start talking about some of the biasing and referencing stuff. And I'm covering it here because actually it will be useful for us in that biasing context as well. So let's say indeed we go and we build one of these two-stage amplifiers. Okay? And let's actually just sort of draw a simple example of one of these. And as you'll see in 1 second, the particular sort of characteristic I'm going to be interested in is how we're going to do the COM mode feedback for this amplifier. Okay? So let's say we have, a simple NMOS input pair, okay, with a PMOS current source load. And of course, I'm going to draw everything in fully differential since we're going to be using the COM mode feedback. Okay, and then let's just say that I use a PMOS second stage. Okay? And then, just for the sake of convenience, I'm going to load that second stage with NMOS current sources. And again, for the sake of convenience, let me go ahead and tie the biases of all those NMOS current sources together. Okay? And so now, if I want to do, let's say, COM mode feedback, one simple way I could do it would be to say, well, let me just grab that output over there. This is, of course, the differential output. Feed it into a couple of resistors to actually get the common mode. And by the way, as usual, you might actually do this with capacitors and not with resistors, but I'm just going to draw it with resistors here for the sake of simplicity. Okay? And then let me go and feed that back to some amplifier, which I'm going to compare against some reference voltage, and use that to feed back to the gate of all of these current sources here. Okay? So now, I intentionally didn't draw any signs on this amplifier yet, because it turns out it's not actually particularly obvious what you should make those signs to be. Okay? So let me draw actually two options, and we can maybe walk through and decide which one we think is the correct one. Okay? So option number one will be that I'll make the signs, and I'll do this in blue, let's say, plus and minus like this. Okay? And option number two, which let's do in black, will be to do minus and plus like that. Okay? So now let's see if we can get you guys to make either some guesses or some votes or something like that as to which one you should actually do. So who wants to pick one of these two as being their preferred one? And by the way, I won't bite you if you get the wrong answer, because it's not actually immediately obvious. So who wants to go with either the blue or the black? Let's just pick one and let's see what happens. Blue. Okay, let's go with the blue. So let's see what happens under that condition. All right. So if we go with blue, let's say from whatever reason, at the output common mode, it moves up. Okay, some cosmic particle came in and it moves the common mode up. All right. So if we have that blue configuration there, the gate voltage here will of course go down, right? So over here at the gate of this PMOS device, that will go down, right? And the output common mode will go up, right? All right, now, is that the end of the story, or does something else happen too? Yeah, exactly. There's also actually, well, is it actually from the first stage, or is it from the second stage? It's from the second stage, right? So the path we just did was like this, right? But there's also going to be a path directly from here to there, right? Okay, so which direction is that going to push the output common mode? Oh, and actually, did we mess something up here? That should have been flipped. Oh, I'm sorry. Yes, there we go. I skipped a step. Thank you. Okay, so if this here goes down, of course this goes up, which of course means the gate of this goes up, and therefore this goes down. Okay? However, as we said 1 second ago, due to that transistor right there, right, due to this transistor here, if you make the gate of that thing go down, actually it will make the common mode go up, right? So now the question is, did we get this blue thing right or wrong? In other words, is this really going to behave the way we wanted it to or not? So by the way, how do we have to decide if it's correct or not? Yeah.
Based on the change in the bias currents at both sides of the first stage versus the second stage, which is just the whole change.
Okay, so when you say the whole change, what exactly do you mean?
I mean that it's not cut in half.
Oh yeah, no, I only drew the arrows on one side here, but assume that it's actually happening on both sides.
I mean the bias current from the first stage is cut in half on both the transistors.
Oh, I see. You're just saying that this might be IB over 2 and this might be IB or something like that?
Yeah, or the other way around.
Okay, you are correct, but let's be a little bit careful about it in that obviously the bias currents here are a little bit different from each other, right? And so it's not immediately obvious whether bias current is exactly the right thing to look at. But let's think about this more generally, or yeah, go ahead.
Seems like the change in voltage for one path, common mode voltage for one path would be much greater than the change in voltage.
Okay, so you said that the change in common mode voltage for one path may be very different than the change in common mode voltage for the other path. Okay, so let's actually be specific about this. Let me do that maybe in black. So let's just say that, I'm just going to say that there's two paths for this thing, okay? There's one path like this, and let me say that that path has a gain of AV1, okay? So in other words, if you wiggle the output of that amplifier there, to get from that amplifier to the common mode output, that has a gain of AV1, all right? And let's say that from here to there, through that second bias transistor, I have a gain of AV2, okay? Now, notice the signs of those two are actually flipped from each other, right? AV1 is, in this case, positive, and AV2 is actually negative, all right? So if we want to make sure that we have overall negative feedback, what needs to be the case in order for this choice blue here to be the right choice?
Is there a different one? I mean, overall, well, I guess it's overall negative feedback from the common mode, right?
It's overall negative feedback from the column mode. Exactly. That's correct.
But you were talking from the gate.
Yeah, so when I talked about AV1, I just did it from this point to that point. That's correct. So, yeah, exactly. So if you want to make sure that this choice in blue is the correct choice, you need to make sure that the magnitude of AV1 is greater than the magnitude of AV2, right? Because in that condition, then indeed, on the net coming back from the column mode, you would actually have net negative feedback, okay? So now, in this particular case, as maybe Samit was hinting at, do we think that AV1 is greater than AV2 or not? In magnitude, of course? Probably. Why is it probably the case? Yeah, there's two stages of gain here, right? I have gain from here, and I have gain from there. Whereas in the other one, I only have the gain from this output stage. Now, having said that, that may not necessarily guarantee that this is the correct choice, right? I can come up with some really weird parasitic condition where that doesn't actually happen to be the case. But in general, indeed, this would be sort of the better choice, so to speak. Okay? Now, having said that, you still have to be a little bit careful here, because notice I haven't really precisely defined this column mode here. I'm just kind of relying on this overall loop, trying to get this reasonably correct so that nothing too bad happens, right? And indeed, because of this sort of constraint that I'm introducing here, if something weird were to happen, the whole system might actually just go completely bonkers if, as an example, AV1 really was, not actually a lot larger in magnitude than AV2. Okay? So, oh yeah.
So you're actually using a pseudo-differential amplifier on the right side. So I think that the common mode voltage on the first stage is actually pretty important to get correct.
That's absolutely correct. So you said that I'm using a pseudo-differential amplifier here. So this column mode voltage here is actually pretty darn important to get the biasing here correct. And that's absolutely correct. That's absolutely an accurate statement. All right?
So wouldn't it just be better to use a different column mode feedback for both stages?
Ah, there we go. So great. So you answered the question I was about to ask, which is, indeed, in this particular example, you're probably actually much better off breaking this connection here and using two completely independent column mode feedbacks for each of the two stages, right? One for this first stage here to actually set the biasing of the second stage, and another for the second stage just to make sure that whatever it's feeding has a reasonable column mode going into it, okay? It turns out that even if you were to make this stage fully differential, meaning that you were to add a tail current source here, like this, you'd still really want to you'd still actually probably want to do two completely independent column mode feedbacks, simply because now if you add this tail current source in, right now it's actually really not obvious which path has more gain, right? Because here I have maybe gain from this thing, but then I attenuate it from the tail current source, right? Whereas in this path, okay, maybe you'll have only one stage of gain, but is a gain times an attenuation greater than a gain? I don't know, right? Depends. Yes?
It's sort of a practical question, but it seems like as you start working things like this and adding more common mode feedback into your circuit grows in complexity a fair amount. Like what are the kind of cases I guess maybe it just depends on what the performance you need, but when do you actually want to do this versus just saying, look, I need to do this, I want to do this the easier way because I introduce more errors and things by having it.
Oh, I see. So I think if I were to rephrase your question, the question was, wow, things are starting to look like they're getting really, really complicated, right? And so do I really actually have to do this, or can I just stick with something simpler? And so the answer I would give is indeed, to the extent that you can keep things simple, you do, right? So whenever you can keep things as simple as you can, that's exactly what you should do. Because as you pointed out, the more complicated you make it, the more chances there are that something goes wrong that you didn't think about, right? That's definitely a very good general design principle. Now, on the other hand, that hopefully also answers the question as to when is it you do the more complicated things. You do the more complicated things when you don't have a choice, right? Where you just simply can't get the performance, the noise, whatever it is, out of something as simple as you originally had made it. Now, having said that, there are ways that you can basically, or if you really paid attention to all the things that we've been talking about, a lot of what we've been talking about has indeed been basically saying, how do you try and make sure that even if you build a more complicated structure, you can still decompose it into these simpler blocks that have as little interaction between them as you can, right? And in this particular example, a really good way of doing that was indeed just split the common mode feedbacks so you can analyze each of them independently of the other one. It's a very good question. All right, great. Any other questions on this? Or? So, by the way, keep this rule up here in mind, because we're going to be using it, maybe not by this lecture, but very shortly again in some of the biasing and reference things. Okay? So with that, let's actually go ahead and move on to the next set of lecture notes, which is, I think, something that some of you may have been fighting a little bit with in this last homework, although we did say that you could use ideal biases, which is, obviously, so far I've been kind of nice to you, and I kept saying that, oh, you can just use some bias currents and things like that to really bias your amplifiers up. But of course, in any real chip, in any real system, you typically have to come up with those bias currents yourselves. Okay? Meaning there has to be some circuit inside of the chip that actually creates that bias for you. Okay? So as I think you've probably already seen, there are tons of so-called constant X circuits out there in the world. And by X, I mean anything from, voltage, current, temperature, whatever you want. Okay? And in all of those, there's a few sort of important considerations that you can think of. Obviously, how much power it takes, how accurate it is, how much rejection it has on the power supply, and so on and so forth. But it turns out that really the most important thing to think about in all of these kinds of circuits, or in all of these kinds of, let's say, problems, is really, what do you actually want to be constant? Okay? Because as we'll see in 1 second, there's lots of things that you can choose to be constant that turn out to actually not be particularly useful for you to be constant. Okay? So let's just do one very simple example. All right? Let's say that we have some very simple differential amplifier, and I'll even make it with a resistive load. Okay, so I just have some, let's say, differential resistively loaded amplifier, of course with some differential pair here. Let's say that I was even really nice to you, and I told you that, you know what, I'm going to give you some constant bias current IB that you can use to actually mirror into your circuit to set its bias. Okay? But so now let me ask you guys sort of a question to see if this is really even a good thing to do. So in particular, let's say that indeed I gave you this constant bias current, but now from whatever reason, your temperature increased. Okay? So I don't know, you went to Arizona or the Sahara Desert or whatever, and you're trying to make a call on your cell phone. Okay? So temperature went up by 50 degrees. So if that happens, what's going to happen to sort of all of the stuff you care about in your circuit? So as an example, just pick some parameter in this amplifier and tell me what happens to it. Okay, you said the noise increases. That's actually absolutely correct, although I guess that's sort of an easy one in the, temperature went up, KT went up, so, there's kind of no way around that. What else? You said GM decreases. That's actually correct. So now why does it decrease? There we go. So just as a reminder, the mobility is proportional to something like T to the minus 3/2. Okay, so if you increase the temperature, the mobility will go down, and the GM will indeed go down. All right, so if GM goes down, what else is going to change in this amplifier? Okay, so the gain will change. Unfortunately, how the gain changes is not immediately obvious. So why did I say that? Yeah, okay, so depending upon what kind of resistor it is, RL could either go up or go down. And if it goes up, who knows? Did it go up more or less than the GM? I don't know. It depends on the kind of resistor you used, right? So gain, not entirely clear. But is there something that's definitely clear which way it moved? Current decreases. Actually, no. Well, so in this particular case, I am using a fixed bias current, so that's not going to change. There we go, the gain bandwidth, right? The GM went down, so the gain bandwidth is definitely going to go down, right? All right, so the point here is that, yeah, you use the constant bias current, but notice even by changing something as innocent as temperature, all kinds of stuff you probably cared about changed, right? In particular, your gain bandwidth went down. And that's probably not what you really wanted, right? You probably wanted the same gain bandwidth at this higher temperature as you did at the lower temperature, okay? So that's kind of bad news, right? And then, by the way, it turns out that particularly for just sort of doing a fixed bias current like this, I can change just about anything that you can think of, and pretty much all of these parameters will change, okay? Reason being that having a fixed bias current really doesn't fix anything about the gain bandwidth, the actual gain, the bandwidth, or pretty much any other parameter you might really care about, okay? So as I said a second ago, the trick with all of these kinds of problems is really to think about what is it that you want to be constant, okay? So as an example, if you want the bandwidth to be constant, you have to come up with a way of biasing the circuit that actually makes the bandwidth constant. Now, as we'll see in 1 second, what that typically implies is that you have to find some physical quantity whose units are the same as what you want to be constant to reference yourself against, right? Because if you think about it, if you want the bandwidth to be constant, there has to be some frequency somewhere that you're referenced against that's actually setting that bandwidth, okay? Now, it turns out there's lots of ways to do transformations between things. For example, let's say I gave you a reference frequency, but you actually wanted, I don't know, a constant gain. Well, how could you sort of take that, how could you take a reference frequency and translate it into something else that would give you a constant gain? What would you have to do? And I don't mean specific circuit details, I mean conceptually. Like, how do you get the units to work out? Yeah, exactly. You have to reference it against some other frequency, where somehow magically that frequency tells you something about the gain you're interested in, so that when you normalize those two things against each other, you have unitless against unitless, right? So again, keep this idea in mind, because we're actually going to play this trick sort of over and over and over again, okay? So let's actually do a real, quote-unquote, constant gain example. So let's again sort of take our simple resistively loaded amplifier, okay? So I'll have my two RLs over here. And this time, instead of having a constant bias current, I'm going to try and come up with the quote-unquote right bias current that will actually give me a constant gain. Okay? So before we do that, we just have to remind ourselves, of course, what is the gain of this structure? What is that set by? Not a trick question, by the way. Yeah, it's just GM times RL. Okay, so now, remember, at the end of the day, what I'm trying to do is fix a bias current that will eventually give me a constant gain. So I'm probably going to have to massage this expression a little bit to actually make it so that, a bias current shows up somewhere. Okay? So in particular, let's say that this is an IB right here. So how might I massage this expression to make it so that an IB actually pops up? Yeah, exactly. Just use V star, right? So in other words, this will just end up being IB over V star times RL. All right. So, okay. So you asked, is there a factor of 2? There's no factor of 2 just because I defined IB as the total bias current and not as the current through each branch. It's a good question. All right. So now notice if what I want to do is make the gain constant, then what I basically have to do is make this IB over V star somehow track RL, right? Or in particular, to say it another way, if you think about V star over IB, the units of that are resistance, right? So what I'm basically saying is I want the resistance, which is set by V star over IB, to somehow track with the resistance of RL, all right? So I claim there's actually a really easy way of doing that. So in particular, if I gave you a V star, so I told you I want this to be the V star, and somehow magically it came from some other circuit, can you tell me how I can build a circuit that would give me the right bias current? Yeah, exactly. I just basically build a resistor. Okay, now I'll do it in a slightly more sophisticated way. I'm actually going to do it in a way that's going to be easy to sort of mirror that current over. So as an example, let's say I give you that V star right there. I'll take some resistor here. Let me just call this RB. Okay? Nicely enough, the signs on this one are easy to get correctly. I'll draw it that way. And then I'll just take that current and I'll mirror it into my actual amplifier. Okay? So notice if this thing is really working the way it's supposed to be, it'll cause V star to show up across that RB, right? Which would mean that I'd have a bias current here, which is exactly set by V star over RB, right? And then if all of my current mirroring is correct, then at the end of the day, my gain will really just end up being proportional to RL over RB. Okay? And of course, there might be some scale factors with current mirror ratios, but don't worry about that. Does this make sense to everybody? Or? So in other words, the trick that I played here is I said, well, look, if I want a constant gain, I know that that GM somehow has to track with a resistance, right? So all I did here is I said, well, okay, fine. I'm therefore going to build the current going into that GM such that the GM just ends up being slaved by a resistance somewhere else, right? And as long as this resistance is built out of the same stuff that this resistance is, everything indeed should track perfectly from a gain standpoint. Make sense to everyone? Or? Now, there's one thing that you should be complaining about here. So what you should be complaining about? Yeah, how in the world did I get V star in the first place? Okay, so turns out I'm going to come back and show you in like maybe 2 slides or so how I would actually get that V star. And it's going to turn out I'm going to get it from the circuit itself. Okay, now if that confuses you, don't worry. It is very confusing. It's a recursive argument. But I'll show you exactly how you actually do it in 1 second. Okay? Before I do that, I do want to just sort of briefly mention that it turns out that with almost all of these sort of biasing things, the number one thing that can kind of screw it up is the power supply. Okay? Because if the power supply varies, then basically it's going to change just about everything, because sort of by definition, any bias circuit you built has to take some power, and therefore it has to be connected to the power supply one way or another. Okay? So the sort of classic way, or the simplest way, let's say, to try and build a supply-independent bias would just be to do something like the following. Okay? So you just take some RB there, and then you use that to sort of set the gate voltage of a diode-connected transistor. And then this is your essentially output current over here. All right? So the trick here is if we're interested in sort of how independent really is this of the power supply, then we can, as usual, just draw a simple small signal model and figure out what the effect of changing the power supply would be on the output current. Okay, so let's go ahead and actually do that. So let's say I have some small signal change in my VDD right here. Okay, I have this RB. Then that current mirror, the diode connected device will just look like a 1 over GM. This, let's just call it some VB. And then I'll have a GM VB over here. And that will be my I out. Okay? So hopefully it should be pretty obvious that if I do this, my VB is just going to be 1 over GM divided by 1 over GM plus RB, right? Times VDD. In other words, it's just a resistive divider. Right, well, then once I've done that, you can then also quickly come up that I out is just going to be GM over 1 plus GM RB times VDD. Okay? So as should hopefully be sort of obvious here, this basically says that the only thing that's really giving me some independence from the power supply is if I can really make the incremental impedance of that diode-connected device there very, very small compared to the output impedance of this RB, right? In other words, I really need to make it so that GMRB is as large as I can possibly make it, okay? Possible, but, you know, there's a limitation there, right? There's only so high I can actually make that, right? Especially given a certain total power supply voltage that I have available to me, right? Okay, so it turns out that much like sort of in this previous example, the problem we have here is that we're not really sort of setting our current based upon what we really wanted it to be, which is in this case going to be a VGS. We're actually setting it essentially by something like a VDD minus a VGS. Okay? So it's pretty clear that because of that, the VDD is always going to show up in some amount onto that output, right? So what I'd really like to actually do is instead of setting my bias current by VDD minus VGS, instead I actually want to set it only by VGS. Okay? So let's just sort of walk through a sort of set of thought experiments as to how we might be able to do that. Okay? So like we had done a couple slides back, let's first assume that somehow magically I gave you the VGS you needed in the first place. Okay? If I gave you the VGS you needed, then you could do something like this, right? You could basically, and this is, by the way, a lot like the sort of gain-boosted Cascode. You could say, all right, if I have the VGS I wanted, then I could take that VGS, I could force it across my resistance, and then take my output current from here, right? And notice the power supply doesn't show up anywhere directly in this picture, right? So now, of course, I've cheated still here because I didn't come up with I don't have a VGS anywhere, right? I still have to sort of come up with what that VGS is in the first place. Well, turns out I can play one very simple trick to actually sort of implicitly get that VGS, all right? And the way I'm going to do it is actually by building the simplest possible amplifier I can think of, okay? So what would be the simplest possible way you can think of to build this, but do it in a single-ended way? How do you just sort of, what's the simplest amplifier we almost always build? Yeah, it's just a common source amplifier, okay? So if I do that, this is, of course, my input. That's, of course, my output. And by the way, notice, magically, what is this voltage here? By definition. Yeah, it's VGS, right? So notice, without actually putting any explicit reference in whatsoever, I'm basically saying, hey, look, I'm going to make sure that a VGS shows up across this bias resistor here, right? Again, this is utterly and completely recursive, but actually does work, okay? Ah, there we go. So you actually, again, answered the question I was going to ask. You said, well, wait a minute. You still cheated, because there's still a bias current source there, all right? So now if this sort of hurts your head, I'm going to hurt your head even a little bit more, because I claim I can actually get that current source for free. So does anybody know how I get that current source without actually introducing any other, let's say, dependencies on anything else? Yeah, exactly. So the thought process goes as follows. It says, well, you know what? If this circuit can generate a bias current for me, why don't I just use that bias current to bias the amplifier? Okay? And indeed, that's exactly what you'll do. So just say, you know what? Let me just take that bias current and use it to bias that amplifier. Okay? And indeed, this is now what's a so-called VGS-based reference. Okay? Yes? Ah, perfect. So you again answered the question I was about to ask, which is, obviously if you do anything like this, you need to make sure that the thing actually starts, right? Because this whole thing is like an inductive process, right? You have to assume first that it exists, and then everything works out. But if it doesn't exist in the first place, guess what? It will also continue to never exist. Okay? So as we'll probably finish sort of next time when we really get further into this, indeed, anytime you do these kind of self-referenced kind of structures, you will typically need some sort of startup circuit just to make sure that there isn't like a parasitic condition where there is no current and therefore nothing actually works. Okay? And by the way to see how that might happen is, if, for example, this voltage here initially started at 0, meaning this transistor was totally off, that would mean there'd be no bias current up over here, and absolutely nothing would happen, right? It would all just sit there and be stuck, right? So the way you have to build these startup circuits, you have to say, well, you know what? If I see that there is no current here, let me kick the whole thing and make sure that there is some current, just to make sure it starts. And then once it starts, I can shut off that kick thing that I did, right? Because I know that it'll then settle to the right spot. Make sense to everybody? Or? Okay, great. So